Okay, we've now completed the necessary mathematical background on vectors to begin mechanics in earnest. As I previously have mentioned, mechanics is the science of motion. Mechanics itself, however, is actually divided into two parts. We first of all have what is called kinematics. Kinematics is the mathematical description of motion. And then secondly, we have what is called dynamics. Dynamics is understanding the causes of motion. Over the course of the next couple of units, you'll be introduced to kinematics and dynamics. Okay, so once again, mechanics, the science of motion. It's divided into two parts. We have what is called kinematics, which is the mathematical description of motion. And as you'll see, mathematically describing motion is not trivial, even for something seemingly as simple as the following: taking an object and tossing it like so as a projectile. As you'll see, mathematically describing such motion is difficult to do. You'll be introduced to kinematics with one-dimensional cases and also two-dimensional cases. And then we also have what is called dynamics. Dynamics is understanding the causes of motion. But for now, we concentrate on kinematics. We start with what is called one-dimensional kinematics. With one-dimensional kinematics, we assume that all the motion takes place along the number line. We think of that number line horizontally as x. Later on in the vertical direction, we'll think of it as y. Kinematics, however, begins with a series of definitions. The first of those definitions is something that we're actually already familiar with for my description on vectors, and that's position. Now, when describing position, say horizontally along a number line, we use the variable x to describe position. It is a vector quantity. However, notice that I am not drawing the vector symbol above the letter x. The reason for that is because when you're talking about one-dimensional motion, all the motion occurs either in the positive direction, to the right-hand side, or the negative direction, to the left-hand side. So then therefore, using the vector notation to describe such motion is considered somewhat redundant. We will, however, adopt the vector notation once again when we take a look at two-dimensional cases. So keep in mind that when I write the letter x to describe position, it is a vector quantity, but we don't necessarily have to write the vector symbol above it for those reasons. Let's say that we take a look at an object when we start the clock. This then means that the object, with respect to an origin, has an initial position. We write initial position as x with a little subscript 0 next to it like so. This is pronounced x naught. X naught refers to initial position. And then some time interval goes by, and then with respect to that same origin, the object ends up with a final position. The final position is just referred to as x. This then means that over the time interval that elapsed, the object underwent a change in position. We always describe the change in a quantity by using the Greek letter delta. Delta x, like so, specifically refers to change in position. Now, the change in a quantity is always equal to, by definition, the final value minus the initial value. So then therefore, change in position is equal to the final value of position x minus the initial position x naught. There is a little bit of tail to tip method of vector addition that is present here in this expression. In order to see how the tail to tip method of vector addition works, I'm going to do here an extra step for us. I'm going to take the initial position x naught and then move it to the other side of the expression. Algebraically, when I do this, this then gives us the following. So once again, this is for the tail to tip method. Initial plus change is equal to final. In order to illustrate this, however, perhaps a little bit more clearly, let's go ahead and take a look at the first of today's lecture examples. Go ahead and copy down that lecture example into your notes now. I've cast it up onto my screen, which is here out of the camera's view. Let me go ahead and read that problem for us. The student is initially 5 meters to the left of the origin. The student then walks 10 meters to the right. In part A, we're asked to calculate the student's, or find rather, the student's initial position. In part B, the student's final position. In parts A and B, the information is actually already given for us. We just have to identify what is what. Okay, so in part A of the problem, it says that the student is initially 5 meters to the left of the origin. That is the student's initial position. That's x naught. We'll write it, however, as negative 5 meters, where the negative sign indicates that the position is to the left of the origin. Okay, and then the student walks 10 meters to the right. So then therefore the student ends up 5 meters to the right-hand side of the origin. This then gives us the student's final position. So that's part B, the student's final position, x is equal to positive 5 meters. In part C of the problem, we're asked to calculate the student's change in position. Change in position is also referred to as displacement. Now let's go ahead and mathematically find the change in position. Once I have done so, then I'll show how the vectors add together by using the tail-to-tip method of vector addition. Okay, so in part C of the problem, the change in position is final minus initial. So I have here 5 meters minus negative 5 meters. That then gives us positive 10 meters. Notice that the change in position here of positive 10 meters is the second sentence in the problem. It says that the student then walks 10 meters to the right. That's the change in position vector delta x. Okay, now here's what the vectors look like on a number line depicting the tail-to-tip method of vector addition. All right, so here is a number line that represents position in terms of meters. Right here we have the origin, and then we'll say 5, 10 to the right, and 5, 10 to the left, like so. Okay, and then we start off by drawing the initial position vector x naught. That's negative 5 meters. That then looks like this to the left-hand side. Like so. And now we place the tail of the second vector, delta x, at the tip of the first vector, x naught. Now right here is the second vector, delta x, the change in position of positive 10 meters. The tail of that vector starts here. I'll draw it, however, below the number line such that we can see it. That then looks like this. And then the final position vector, x, that's the resultant of these two, the final position vector x goes from the origin, ultimately then to where we end up. In this case, 5 meters to the right-hand side. So then therefore the final position vector x looks like this. So we would then pantomime the tail-to-tip method of vector addition for these position vectors in the following way. The initial value plus the change is equal to the final value, like so. So initial plus change is equal to final. Okay, let me go ahead and erase. Okay, now continuing with our kinematics definitions, we now get to two words that we tend to use somewhat interchangeably in everyday language, but mathematically they are not the same thing. That is speed and velocity. We'll take a look at these average quantities first. First of all, average speed. Okay, average speed is denoted as the letter V. There's a subscript S next to it to indicate speed, and then we put a bar symbol above like so. The bar symbol specifically means average. Now, by definition, average speed is equal to distance divided by time. Notice that I have here an extra slash associated with this equals sign. In mathematical notation, the extra slash means by definition. So by definition, Average speed is distance over time. Sometimes we just write this as d over t. Now, distance is a magnitude. It's just a length. There is no direction associated with distance. Distance is a scalar quantity. Time is just a number. That's also a scalar quantity. So then therefore average speed is a scalar. Okay, now distinct from that mathematically is what is called average velocity. Once again, we tend to use the words speed and velocity interchangeably in everyday language. They're not the same thing. Average velocity is written as v with a bar symbol above it. Once again, the bar means average. And then by definition, this is equal to change in position divided by change in time. Notice that the numerator of the expression, the change in position, is a vector quantity. So then therefore, average velocity is a vector, unlike average speed, which is a scalar. At this point, however, I should probably mention the following: exactly what is meant by time. Well, that's basically a question that's at the forefront right now of 21st century physics, exactly what is meant by time. We are nowhere near that point, however, here in this course, so then therefore you can merely think of time in the following way. Time is something that clocks measure, and that is good enough for our purposes. Now let me illustrate the difference between average speed and average velocity with the next example. I have to move it down on my file. Okay, copy that problem down into your notes. The problem reads as follows. In the previous problem, the one that we just completed, the total time elapsed was 10 seconds. What was the student's average speed in part A? What was the student's average velocity in part B? Let's take a look at that. Okay, now in the previous example, if you recall, we had the following. The person started 5 meters to the left-hand side, walked 10 meters to the right-hand side, and then ended up 5 meters to the right-hand side. The total distance walked by the student was 10 meters. The change in position delta x, however, that was equal to positive 10 meters. Notice the plus sign there for clarity, indicating that this is in fact describing a vector quantity. So then therefore the average speed, which is distance divided by time, is 10 meters divided by 10 seconds. Now numerically, of course, this is just equal to 1, but how do the unit symbols behave? Recall perhaps from chemistry class or from an earlier science class that unit symbols behave like numbers. So what we're doing here is we're taking meters and dividing it by seconds, and we leave it at that. We leave it as 1 meter per second. Now numerically, I'm going to calculate the same value here for average velocity. Average velocity, v bar, is change in position divided by change in time. This is positive 10 meters divided by 10 seconds. This is equal to positive 1 meter per second. This is, however, a vector quantity, so then therefore we could represent it graphically. When I do represent it graphically, however, I cannot represent it on a number line that describes position. Instead, velocity has to have its own number line. So for example, right here is a number line that describes velocity in terms of meters per second. Right here we'll say is 1, and then therefore the average velocity vector is as follows. Notice that the average speed and the average velocity are easy to calculate. However, neither of these quantities tells us exactly what happens at an instant in time. For example, if we were going to describe the motion of a projectile, as we will later on like so, in order to completely describe this motion, we would have to describe exactly what happens at an instant in time. I will begin to describe that in part 2 of this lecture.